Hi everyone, our topic for today is about tangent vectors and normal vectors. So in this lesson, you should be able to find a unit tangent vector and a principal unit normal vector at a point on a space curve. So let me start by defining what a unit tangent vector is. So let C be a smooth curve represented by R on an open interval I. The unit tangent vector denoted by T of t at any time t is defined by this equation. T of t is R prime of t over the length of R prime of t provided that R prime of t is not equal to 0. So we know from the previous discussion that a curve is said to be smooth on an open interval when R prime is continuous and non-zero on the interval. So this indicates that smoothness is sufficient to guarantee that a curve has a unit tangent vector. Okay, so suppose we have this example. We are asked to find the unit tangent vector to the curve given by R of t is ti plus t squared times j when t is equal to 1. So to find the unit tangent vector, we need to get the first derivative of R of t. So the derivative denoted by R prime of t is the derivative of the first component, which is 1 times I. So we have I plus the derivative of the second component, which is 2t, derivative of t squared, times j. So this is the derivative of R of t. And after that, we divide the first derivative by its length. So we have R prime of t, which is I plus 2tj, divided by the length of R prime of t, which is equal to the square root of the sum of the squares of the first component plus the square of the second component. So you have 1 plus 4t squared. And then we need to find the unit tangent vector to this curve when t is equal to 1. So we have to replace all the t variable by 1. So t of 1 is 1 I plus 2 times 1 is 2 times j. So you have I plus 2j divided by, because t is 1, so 1 squared is 1 times 4 is 4 plus 1, so we have 5. So we have square root of 5 in the denominator. So therefore, the unit tangent vector to this curve when t is equal to 1 is I plus 2j over square root of 5. Okay, recall that the equation of the curve in vector form is R of t equals t of I or ti plus t squared j. So this indicates that the x component of this vector valued function is x equals t and the y component is y equals t squared. So this is the corresponding parametric equations of the components of this vector valued function. So from y equals t squared, because your x is t, so by substitution, y is equal to x squared. And at t is equal to 1, the x coordinate is 1, the y coordinate is 1. A parabola, which is opens upward, vertex at 0, 0. So this is the vertex that if x is equal to 1, your y is 1. If x is negative 1, your y is 1. So connect these points, the origin and these 2 points. So you now have the graph of a parabola. So we need to find, or we need to sketch the unit tangent vector when t is equal to 1. So at t is equal to 1, the x and the y coordinate are both equal to 1. So this is the initial point of the vector. And since the unit tangent vector has these coordinates 1 over square root of 5 and 2 over square root of 5. So 1 over square root of 5 is approximately 0.44. So from x equals 1, you scale 0.4 units. Okay, so this is when x is 0.4. And then for the y coordinate, which is 2 over square root of 5, this is approximately equal to 0.89. So from y equals 1, you scale 0.8 here. Okay, so this point therefore is the point 1 over square root of 5 and 2 over square root of 5. So connect the initial point and the terminal point. So this is now the unit tangent vector when t is equal to 1. Okay, from the unit tangent vector, let us now define the tangent line to a curve. The tangent line to a curve at a point is the line that passes through the point and is parallel to the unit tangent vector. In example number 2, the unit tangent vector is used to find the tangent line at a point on a helix. Okay, so as an example, suppose we are asked to find the unit tangent vector denoted by t of t, and then we need to find a set of parametric equations for the tangent line to the helix given by this equation. R of t is 2 cosine t times I plus 2 sine t times j plus tk. At this point, square root of 2 square root of 2 pi over 4. So to find the unit tangent vector, now we need to find first the derivative of r of t. So r prime of t equals the derivative of cosine, which is negative sine t times 2. So you have negative 2 sine t times I. Next, derivative of the second component, which is sine t. Derivative of sine t is cosine t times the numerical coefficient of 2. So we have 2 cosine t times j plus the derivative of t, which is 1 times k. So you have k. So therefore, the first derivative of r of t is negative 2 sine t times I plus 2 cosine t times j plus k. Then after that, we need to find the length of the derivative of r of t, which is equal to the square root of the square of the first component, so 4 sine squared t, plus the square of the second component, which is 4 cosine squared t, plus the square of the last component, which is 1. But recall that sine squared t plus cosine squared t is 1. Now you factor out 4, and then the remaining terms, such as sine squared t and cosine squared t, when added is 1 times 4. So you have 4. Now plus 1, so we have a square root of 5. So the length of the first derivative of r of t is the square root of 5. So therefore, the unit tangent vector is the derivative, which is r prime of t, over the length of r prime of t. Okay, so from here, from the previous slides, this is negative 2 sine ti. Okay, that's the first component. And then for the second component, you have 2 cosine tj, and plus the third component, which is k, divided by the length of the first derivative of r of t, which is square root of 5. So at this given point, square root of 2 square root of 2 pi over 4. So at t is equal to pi over 4, the unit tangent vector is obtained by replacing all the t variable by pi over 4. So we have negative 2 times sine of pi over 4 is square root of 2 over 2 times I plus 2 times cosine t, but if t is pi over 4, cosine of pi over 4 is also square root of 2 over 2 times j plus k. Because 2 is common, so you cancel this out. So you have negative square root of 2i plus cancel this out. So you have square root of 2 times j plus k divided by square root of 5. So the unit tangent vector at t is pi over 4 is 1 over square root of 5 times negative 2i plus square root of 2j plus k. Okay, from the first derivative of r of t, we can find the direction numbers a, b, c, where a is negative square root of 2, b is square root of 2, and c is equal to 1. So using these direction numbers and this given point x1, y1, c sub 1, we can obtain the parametric equations of a line. Recall that the parametric equations of the line is x equals x sub 1 plus as, or in some book they use x sub 0 plus at, where t is any parameter. Y equals y sub 0 plus bt, and c equals c sub 0 plus cs. But here, we use x1, y1, c sub 1 for the point, and ab and s for the parameter. So the parametric equations of the line is x equals x sub 1, where x sub 1 is square root of 2 minus or plus a, where a is negative square root of 2. So you have negative square root of 2 times s. y is equal to y sub 1, where y sub 1 is square root of 2 plus b, which is square root of 2 times s. And c equals c sub 1, where c sub 1 is pi over 4, plus c, where c is 1 times s. So these are the parametric equations of the line. Okay, so in summary, the unit tangent vector t of t on the curve c is given by this equation, that the t of t is equal to r prime of t over the length of r prime of t, provided that r prime of t is not equal to 0. So r of t here is a vector valued function, or this is the equation of the curve.